Hello and welcome to another tutorial. Today we're going to have a look at the differential line growth that I implemented for the brain shape. And this one is made of two components. The first one is the line growth itself, and then we extrude the strand and collide it with itself to get this collision going on. But for now, let's concentrate on the strand. I'm just going to disconnect the mesh. And have a look inside. There is another collision to confine everything to the shape that I modeled. We don't need to worry about this as well, so just look at the line growth itself. And there are two different nodes that we need to look at. It's the point relax in the first place. This is going to push the points away from each other based on the distance that we put in. And if we disconnect the displace and just look at the flat 2D circle, and this is what we're getting. So let's build it from scratch. Get a new scene. Create a nerve circle. Then we get the point position of the strand, and we want to get the neighbors of each point. So we can use get points in radius node. And what this will give us is an index array for each point. And since we want to loop this a couple of times, we can create the iterate node and put that in. And also the radius, since this is the parameter we want to adjust. And the max iterations as well. So once we have all our points and the neighbors, we make a for each loop and iterate over the neighbors. So make that an iteration target. We don't need the max iterations, we're going to go through all of them. And then we get from array all the point positions of the neighbors. And we're also getting the point position of the current point we're looking at. And what we want to do is this. Let's say we are looking at a point, and within a radius of 2 units we find 2 neighbors, and the neighbors have a distance of 1.5. And the difference between the search radius and this value is 0.5, and we want to push our point 0.5 units away from the neighbors. So this neighbor is going to push our point in this direction, and this neighbor is going to push our point in this direction. So we end up with 2 projected point positions here and there. And then we're simply going to take the average of the projected points somewhere in here. And that's the point that we're gonna use. So let's implement it. We can first subtract the points, the neighboring points from our current point, which is a bunch of vectors. And then we get their length. And then we compare the length. So if the length is less than our search radius, let's hook this up. Then we want to push the point, and otherwise the point can stay where it is. And to push our point, we're going to normalize the vector and then multiply it with the difference between the radius that we're searching and the actual vector length. So we're subtracting the length from the radius, multiply with the normalized vector, and add it back to our original point position. And since we have multiple neighbors, we want to average the projected points. So you can use the average node from Valhalla, or we can do it ourselves by summing up the array and dividing it by the size of the array. So get the size of the array, convert to float, and then we have our new point position. Yeah. We should actually, yeah, that's fine. Put out the point position and then set point position on the geometry right here. And since this is an iterator, we'd have to set the state port state. And have a look at what it's doing. So now, if we increase the iterations, it's going to push the points apart up to 2 units right now. And then we only need to put in new points. So we sample the strand, and the spatial distance should be a little bit smaller than our radius. 0.05 is a bit much. Well, let's say 0.5. And then we're already getting our differential line growth. Cool. So if we then displace our input nerve circle, let's take a turbulence field, then we're already getting a nice 3D shape. And that's the first part of the tutorial. The next part is the SDF collision. And to show this, I'm going to hide everything that we did so far and create a new compound. And we're going to create a sphere, maybe with some more divisions. And a locator. So I can show you what this signed distance field is actually doing. Get the sphere into our board, and to get in the position of the locator, I'm going to construct points, make it input node, and hook everything up in the node editor. So get the locator translation, and hook this up to the point position. We convert the mesh into a level set. And you can see the volume. And if we check our data flow, we can see that there is a voxel signed distance float array. So for each voxel, the signed distance is the distance between that voxel and the closest point on the mesh surface. And to show this, I'm going to sample the volume. At our current locator position. And I'm going to pass the geometry through this node. I'm going to use it quite a lot. And I have a handy little compound to show numeric float values. So I'm going to set the geo property called signed distance on our point, and then show it as a numeric value. I forgot to put in the voxel signed distance property into the sample volume node. So we're sampling voxel signed distance in our field or level set, and then put that value onto our point geometry. And then we're seeing that outside of the sphere we are having positive values, a value of 2, a value of 1, and then we're getting closer to the surface of the input mesh, and there it should be 0. And inside of the sphere we should see negative values, so minus 1, 0.6, minus 2, and so on. And then we can use a gradient field to give us the direction that we need to push the points to get onto the outside of the surface. So we sample volume gradient. Get the signed distance. And this is an array of flow 3, so a vector, and the vector is pointing towards the greatest increase in the signed distance field. So since we're having negative values here inside the sphere and a value of 0 on the surface of the sphere, all the vectors are going to point outside. And we can show this by setting geo property again. Make that a flow 3, call it gradient, and get a point scope out. We're already seeing the point itself. And we're going to show arrows of the gradient. There it is, that's our direction. It's pointing towards the greatest increase in the sign distance field. And then we can normalize this vector and multiply it with the distance. Let's put that into our gradient property. And then it's just a simple matter of negating the sign distance to get the correct vector. So we negate the distance before we multiply, and then our vector can bring our point inside the sphere right back onto the surface. Or if we want, we could also push points that are outside the surface back onto the surface. This was what we're actually doing in our demo. But you can use the SDF collision compound everywhere you like, so let's make this a little bit more general purpose. So we can set the point position of our incoming mesh, and we can make an if statement right here. And for a general purpose compound, you want to query all the points that are inside our collision object. So if the sign distance is less than 0, so negative, it is inside the sphere. And in that case, we want to push our points outside. So we're getting the original point position and adding our vector. And otherwise, the point is going to stay where it is. Set the point position, and then output this whole thing. We can have a look at that point, make another scope. So if we are outside of our sphere, the point is going to stay where it is. And if our sign distance is less than 0, so if we're inside, the point is going to be projected back onto the surface. Great. So once we have our SDF collision node in place, we could actually go ahead and work on our differential line growth compound. I would like to show you something else. Let's create another sphere and use that sphere as a second mesh to collide with. And if I hide the sphere, you can already see that our collision is working. But all the points that have been pushed could do some kind of relaxation or mesh smooth. And we can identify the points by subtracting the original position, or the new position from the original position, and build a delta. So there's our original position, and there is the new position after collision. We can call this delta. And since some of these points might have been pushed pretty far, we want to normalize these values. So put this in a proper range of 0 to 1. And to find out what the minimum and maximum values in this array is, we should get the length, by the way. We can use array bounds. And I'm going to look up the max bounds to from end. So we're getting values from 0 to 1. And then set that as a property. Call it delta. It's a float. And maybe at this point we can make that a compound. So get everything, put that into a compound. That's the SDF collision. I'm not going to need the locator anymore. Get rid of it. So now that we have our delta, let's have a look at it. Make a point scope. I'm going to look at delta. So this is the mask we're getting. And with that mask we could drive some kind of relaxation. And to make this real quick, we can use the point position for our geometry, and then for each point get all the neighbors. Update point neighbors. It's a REPL pack node, and it's going to check for the connectivity of each point and spit out an array of indices again. It's just like the get points and radius node. So then we're going to loop through all the neighbor positions. Make it an iteration target again. Get the point position of all the neighbors and average. This time we're going to use Valhalen's average array node. Put out the point position and set point position. And this is going to relax all the points, but we only want to use the points that have the delta mask. So we can loop the original point position to the average point position by our delta mask. So we're getting the geo property delta, which is a float. And then, since the fraction in the lerp is going to use a vector, we convert the scalar value of delta to a vector 3 and use that as a weight, basically, to only relax these points. And if we want, we can also make this a couple of times, so we can iterate. Everything out. Set part state. Let's call this mesh smooth. And then we can do this a couple of times. Right, and if you like, you can also incorporate this into the self-collision compound and make this a little bit more general purpose. And then maybe get an input node and hook up the max iterations. So you can adjust it on the fly. And the cool thing is you can introduce a couple of other nodes, like Maxime's node to smooth any property. So smooth geo property. And if you want, we can smooth the delta. There. And change how our smooth is behaving. And then what we can also do is have multiple meshes combined and collide with itself. There are a couple of things that we need to do to get this going. So we build the array of meshes and then merge them. And hook them up with as a mesh and the collider mesh. And then there is only one or two things that we need to change in our compound. So first of all, in the meshed level set, we don't want any thickening. And then to make the self-collision a little bit more robust, we should increase the minimal hole radius just by a tiny bit. And then we're getting self-collisions. Nice. Okay, so now that we have a working self-collision compound, we can copy that over to our first graph. Hop into our relax node. Right after introducing the new points, we can collide them with a geometry of our choosing. But remember, right now we're pushing points away or onto the outside of the surface if they are inside. But what we actually want to do in this case, let's take one of our spheres as a collision object. What we want to do is push all the points that are outside of our sphere back onto its surface. So in our collision compound, we have that if statement where we had a look at the assigned distance values, and if they are smaller, so inside of our collision object, then we are pushing the points. But we can also reverse it and have a look at if our voxel assigned distance is greater than 0, then we're getting all the points that are outside of our sphere and pushing them back onto the surface. That's what we want to do. As for the smooth of the delta and everything, the smooth is not going to work on the strand because the update neighbors node is only working on meshes, I think. But we don't need it for now, so we can just bypass it. So we connected our strand, but that didn't connect is the sphere. So this might take a while, but it works. So now we are growing our strand until it's outside of our sphere, projecting the points back onto the sphere, and then with the next iterations the points are going to be pushed apart again. Maybe we can decrease the voxel size to make it a little bit faster. And the collisions. Yeah, that's how you confine it. And this is all there is to it, really. We have our shape, and we can maybe extrude it. Use Maxim's extrude strand compound to get a mesh. The size might be a little bit too big. Yeah, maybe something like this. 0.5. 0.6. It's fine if they're self-colliding, because now we can make use of our SDF collision node again. Maybe get the other one. We have our smooth still in place. I'm going to pipe out the smooth geo delta iterations as well. Yeah, and there it is. Maybe we can decrease the smooth again. Then we're getting proper self-collisions on our differential line growth extrude. You could also resample the strand right before extruding to get a little bit more fidelity. But that's it. That's all there is to it, really. So have fun with it, guys.